Today we're going to start out with a couple of quizkins that have to do with the Clausius-Clapeyron equation and a consequence of what we know about vapor pressure. And then we're going to move on to talk about solids for the rest of the day. We'll talk about how solids are packed together and look at three common forms of crystals. Then we'll talk about the difference between crystalline solids and something else that we think of as solids that maybe necessarily aren't to be considered solids. And then last of all, we're going to look at a theory of bonding in solids that takes molecular orbital theory kind of to a new level. So let's start out first of all with this quizkin. This quizkin starts out with this question. Chloroform, the formula is CHCl3, has a normal boiling point of 61.62 degrees C and a molar heat of vaporization of 59 calories per gram. It's an unusual unit, so we'll have to think about what to do with that. The question is, what is the vapor pressure of chloroform at 25 degrees C? Well, here are some things that we know. We know a temperature. We could maybe call that T1. And we know that that's the temperature of its normal boiling point. Well, the normal boiling point corresponds to a pressure, we'll call it P1, that would be equal to 1 atmosphere, because that's what normal boiling point means. The vapor pressure is equal to 1 atmosphere. And delta HVAP is 59. So we know delta HVAP, we know a temperature, and we know a pressure. The Clausius-Clapeyron equation should allow us to calculate a new vapor pressure if we know a second temperature, which we do, because 25 degrees C forms T2. So at this point, I think you should know that the Clausius-Clapeyron equation could solve this problem. It might be difficult, but with a little algebra skills, you should be able to do it. So stop the video here, and I'll bring you back an answer and a solution in a little bit. Okay, I've reproduced the data here. Pressure is 1 atmosphere. We're going to assume infinite number of sig figs. The first temperature is 61.62 degrees C. Of course, we're going to need that in absolute terms, so if I add 273.15, I get 334.77 kelvins. So that's our first temperature. Second temperature is 25 degrees C. And again, I'm going to assume that that's a target, so I'm going to give it as many sig figs as I need, and I'll convert this to kelvins and make it 298.15 kelvins. Now, the Clausius-Clapeyron equation said this: the natural log of P1 minus the natural log of P2 is equal to minus the molar heat of vaporization over R times T2 minus T1 over T1 times T2. What we want here is P2, so let's begin solving for that. I can subtract P1 from both sides, and this leaves me with minus natural log of P2 equals delta HVAP, negative delta HVAP, over R times T2 minus T1 over T1 T2 minus the natural log of P1, because I subtracted that from both sides. I'll divide this equation through by -1, so it's positive natural log of P2, positive delta HVAP over R, and plus natural log of P1. I think I'm ready to put numbers in here, except the delta HVAP is not going to work out, because I know I'm going to have units of joules per mole, Kelvin, and R, so calories per gram aren't going to work. So I'm going to do a little unit conversion. Delta HVAP. It tells me in the problem that this is 59.0 calories per gram. Well, a calorie is 4.184 joules. If you didn't know that, you could have looked that up. This substance has a molar mass of 119.378 grams per mole. So with this conversion in place, calories and grams cancel out, and I will get my delta HVAP in joules per mole. I get three significant figures here, and it comes out to 29,500 joules per mole. So, plugging my information in here, natural log of P2 is equal to 29,500 joules per mole divided by R. We're using the physics R of 8.314 joules per mole Kelvin. And that's going to be multiplied by T2 minus T1, so 298.15 kelvins minus 334.77 kelvins divided by T1 times T2. So 334.77 kelvins times 298.15 kelvins. And then minus the natural log of 1 atmosphere. Well, that simplifies nicely because the natural log of 1 is 0, so that term just goes away. Now let's crunch down some numbers. The natural log of P2 is equal to, unit-wise, joules per mole are going to cancel out, and I'll have 1 over kelvins. So that's just kelvins. Numerically, 29,500 divided by 8.314 comes out to 3550 kelvins to 3 significant figures. 298 minus 334.77 comes out to a negative 36.62 kelvins. And when I multiply the two temperatures in the bottom, I get 99,812 kelvins squared. When I multiply the two kelvins together, I get Kelvin squared on the top, so that cancels with the Kelvin squared on the bottom, and I end up with a unitless number. When I multiply these things together, the number I come up with to 3 significant figures is minus 1.30. So to find P2, I'm going to take e to both sides. So that's e to the minus 1.30, and that comes out to 0.27, and the units of pressure that we started with were atmospheres, so that's the unit we'll end up with. This quiz kit is a follow-up on that last question. It says 250 milliliters of chloroform are put in a sealed 55-gallon drum at 25 degrees C. Chloroform is normally a liquid, and so that's the state that this is going to be in when we put it in the drum. Of course, it'll immediately begin to vaporize. Then the question is, will any liquid remain once it reaches dynamic equilibrium? Now we have some information here. Density of chloroform is given to us, 1.489 grams per milliliter, and 1 quart is equal to 0.946 liters, so that's a kind of a conversion factor. Well, essentially, this is what we have to think about. We've got this drum. In the bottom of the drum is a little puddle of chloroform. That chloroform is going to vaporize, particles are going to leave and enter the gas state until it reaches dynamic equilibrium. When it does, the question is it all going to be gas? Will it never reach dynamic equilibrium, or will there still be some liquid remaining? We already know what the pressure is going to be when it reaches dynamic equilibrium because we solved that in the last problem. It's going to be 0.27 atmospheres. And the gas laws allow us to tell what the number of moles will be in a container if we know pressure, volume, and temperature, which we do. So we can figure out how many moles of gas will be in here and then compare that with the number of moles of gas that are in the liquid to start with. Stop the video, give this a try, and then I'll give you an answer in a little bit. So let's start out with a little sketch. Here's my drum. In the bottom of my drum is my puddle of chloroform. What I know about the chloroform is that I have 250 milliliters of it, and I also know its density is 1.498 grams for every milliliter. I also know the volume of the drum. The volume of the drum is 55 gallons. And I know the temperature inside this drum is 25 degrees C, which I'm going to assume to be 298 kelvins. And the strategy was, we're going to find out how many moles of gas are present by using the ideal gas law, which says PV divided by R times T. Well, we know what the pressure is. The pressure in here is the vapor pressure when it reaches dynamic equilibrium, the equilibrium vapor pressure. And in the last problem, we calculated that to be 0.27 atmospheres. What's the volume? Well, the volume is 55 gallons, but that's not the volume we want to put in here. So let's convert. 55 gallons, and every American should know that 1 gallon consists of 4 quarts, and our conversion factor said that there are 0.964 liters in every quart. So with quarts and gallons both canceled out, this tells us the volume of this drum in liters. We have two significant figures, and it's 210 liters. So that's what we're going to put in here for volume. R is going to be 0.0821 liter atmospheres per mole Kelvin. And the temperature was 25 degrees C, or 298 kelvins. And so, as we typically did when we were doing these gas law problems before, you see everything cancel out nicely, and this is going to leave us with a number of moles of gas, chloroform. Do the calculation to two significant figures, we get 2.3 moles. So that's how many moles of gas are present. How many moles of chloroform were there in all? Well, I know I started out with 250 milliliters of liquid chloroform. And I know that the density of the liquid was 1.498 grams per milliliter. So now I know how many grams of liquid chloroform were in there. Chloroform has a molar mass of 119.378 grams per mole. So with grams canceled out, I now know how many moles total were in this container before it began to vaporize. I do my calculation, and I find the answer to be 3.14 moles. So the answer is yes, there still is liquid in here. I put 3.14 moles into the container to start with, and only 2.3 moles will be vapor when we reach dynamic equilibrium. So the answer is yes. And how much is remaining? Well, it's 3.14 minus 2.3, which means 0.8 moles of liquid remain. The next thing we're going to do is take a look at a few crystalline forms, some common ways that atoms stack together when they form crystals in solids. The simplest kind is just called a simple cubic. The simple cubic has one atom centered at each corner of a cube. So you can imagine any one of these spheres here. Let's say we're talking about this sphere or this sphere. It's been cut in half once to make this face, another time to make this face, and then a third time to make this face down here. So you cut it in half, that's a half. Cut the half in half, that's a quarter. Cut the quarter in half, that's an eighth. So at each corner of this cube is an eighth of a sphere. And there are 8 corners in a cube. So that means a simple cubic has got one atom per cell. Now, of course, this is only one representative cell. There are going to be many, many atoms stacked together, but every unit cell has only one atom in it. One of the kind of questions that you might be asked to solve on homework problems and things like that involves finding how big the edge is, or finding how many atoms are in a cell, or maybe calculating an estimated density for the substance. So you need to know something about how these things stack in here. I'm going to clear this out and then make a little sketch on here. Let's call an edge S on these spheres. So this is a cube, so it's S by S. In a simple cubic, every edge consists of 2 atoms touching each other at their outside edge and terminating in the corner at a radius. So this is a radius of an atom here, and this is another radius of an atom here. So the edge length, or the side length on a simple cubic, is equal to 2 times the radius of the atom. Keep that in mind. That might be helpful in solving some problems. The next type we're going to look at is called a face-centered cubic, FCC for short. And a face-centered cubic has got, per unit cell, 1 atom centered at each corner. So again, we have an eighth of an atom on each corner. But in addition, centered in the middle of the face of each side is 1 atom. Now that atom's been cut in half. So if we calculate the total number of particles in here, we've got 1/8 at each corner. So 1/8 times 8. And then at each face we have 1/2. But there are 6 faces in a cube, so 1/2 times 6. 1/8 times 8 is 1. Half of 6 is 3. So that means there are 4 atoms in every unit cell. I'm going to clear this out again and talk about geometry. Here's a side or edge length S. Here's another edge length S. In a face-centered cubic, the atoms touch each other across the diagonal. So I'm drawing a diagonal across here, center of an atom here, center of an atom here, center of an atom here. So across this diagonal is one radius, another radius, another radius, and another radius. So across this whole diagonal is 4 times a radius. Now if we follow the Pythagorean theorem, s squared times s squared is going to give us 2s squared when we add it together. So the length here is the square root of 2s. So the square root of 2s is equal to 4 times a radius. Again, that might be useful in solving problems. The last form we're going to look at is called a body-centered cubic. A body-centered cubic has got one atom in the very middle, and surrounding that are 8 atoms, one on each corner of the cube. So the number of atoms per cell is going to be, first of all, that one that's in the middle, and then again we have 1/8 at each corner times 8. So that means we have 2 atoms per cell with this type of a crystalline form. I'm going to clear this out. And now we're going to look at the geometry. Now this one's a little more complicated because the edges don't touch on the edge or the face diagonal. They touch on the interior diagonal. So that means I'm starting here at this corner and I'm going down to this other corner way down here. So I'm going to try and sketch that line through here. Goes right through the center of that body-centered atom. So it's going to be one radius to here. That's the edge of that inside one that we can't see. And then the middle of the atom is there, so there's a radius, and then there's another radius. That's the body-centered one. And then that goes out to that edge, and then there's another radius cutting from the outside edge here through there. It's kind of hard to visualize. Well, to find out how long that length is, that's going to be 4r. But we have to look at a triangle that actually cuts through this thing. So here's one leg of that triangle. It's the diagonal across that top face. And of course we know that that's equal to square root 2s, because this is s and this is s. So Pythagorean theorem tells us that that's what that length is. And this edge is just s. So that triangle that's in the middle there, here's what it looks like. Across the top is square root 2s, and down this side is s. And so what's the length of this diagonal here that's equal to 4r? Well, Pythagorean theorem says add up the squares of both sides. So square root 2s quantity squared plus s squared. Well, that's 2s squared plus s squared. That adds up to 3s squared. So if I take the square root to find the hypotenuse, I find that it's equal to the square root of 3 times s. So the square root of 3 times s is equal to 4r for a body-centered cubic. Again, that may come in handy to solve some problems of some kinds. In a real ionic crystal, it's slightly more complicated than that in many cases because we've got 2 ions that have to fit in there. So if you look at this pattern, you can sort of see a face-centered cubic by taking a unit cell right here. And so the larger green chlorines are arranged in a face-centered cubic. The smaller purple, in this case sodiums, fit also into a face-centered cubic, but they are in the spaces in between. So here's a unit cell for sodium, and you can see the face-centered cubic. It's like the 5 on a pair of dice. One on each corner, one on the face. Same for the green, one on each corner, one in the face. So it's slightly more complicated for ionic compounds. Now that we know what the crystalline forms are like, it would be nice to know what's there. What are the spheres that were in those generic shapes that we looked at earlier? And this is actually very important because it determines what the characteristics or properties of the solids are going to be. So we're going to divide these into several different categories of solids. The first one we're going to look at is ionic solids, like we saw in that last slide. In ionic solids, the particles that are at the lattice sites are ions. And what holds the whole crystal together is ionic bonds. So the attractions of sodium for chlorine, for example, in that salt crystal that we looked at. The properties of these ionic solids have to do with the strengths of the bonds that hold the crystal together. So ionic solids tend to be, because ionic bonds are strong, very hard. They tend to be brittle. They're going to break along lines of plus and minus through the middle of that crystal. They're going to have very high melting points because you have to break ionic bonds to get the thing to melt. And they're not going to conduct electricity as a solid. A characteristic of a conducting substance is that it has to have charged particles that are able to move. Well, an ionic compound is obviously made of charged particles, pluses and minuses, cations and anions. But when they're in the crystal, they can't move, and so it can't conduct electricity. If you melt it, you allow them to flow. They're no longer in the crystal, and then it will conduct electricity. So melted salt conducts electricity. And the same thing is true for an aqueous solution. If you dissolve the crystal, it gets torn apart, and the individual ions exist in solution, and so they're free to move around, and then it will conduct electricity. Another type of crystalline solid is a molecular solid. In molecular solids, the molecules are the particles that are at the lattice sites. So the little spheres in those generic unit cubes would be molecules of sugar or water or something like that. What holds the crystal together then is intermolecular forces. Now, intermolecular forces are much weaker than ionic bonds, and so we can expect to see different properties for molecular solids. They tend to be soft. They tend to be brittle, like ionic compounds, because they do have definite fault lines and they're definitely crystalline. They have a low melting point because the intermolecular forces don't hold them together that much. They are non-conducting as a solid because the particles can't move, but they're also non-conducting as a liquid or as an aqueous solution because molecules aren't charged. They may be polar, but they don't carry a charge, and so they won't be able to conduct electricity in any circumstance. Another type of solid is called a covalent network solid. In a covalent network solid, non-metal atoms are the particles that are at the lattice sites. And typically you're going to find that crystalline solids consist of carbon, diamond, that's an example of a crystalline solid, and SO2. These are probably the most common covalent network solids. Silicon also makes a covalent network solid. What holds the crystal together is covalent bonds. So these aren't like IMFs. They're not hydrogen bonds or London forces. They're actually bonded to each other with covalent bonds. So there's this network of, say, in carbon, for example, every carbon is actually covalently bonded to 4 other carbons, and it makes this pattern that extends throughout the crystal. I'm drawing it flat, but it really wouldn't be flat. It would be three-dimensional because these are all sp3 hybridized. So you get this three-dimensional crystal that's held together by covalent bonds. Covalent bonds are very strong, much stronger than any kind of IMF. So the properties of covalent network solids are they're very hard. Think diamond. They're very brittle because you have to break covalent bonds along the covalent bond lines, and so they're going to shatter. They're not going to smush around very well. They're going to have extremely high melting points because you have to break all these very strong covalent bonds to make the thing melt. And they don't conduct as a solid, and they don't conduct as a liquid because there are no charged particles that can move around. The last type of crystalline solid we're going to look at is metallic solids. In metallic solids, metal nuclei are the particles. And there are covalent bonds, sort of, that hold the crystal together, but they're delocalized covalent bonds. There are several ways of describing this, but the basic idea is that the metal nuclei and the non-valence electrons sit at the lattice sites. And then the valence electrons are sort of shared by all the nuclei, and they float around the crystal and keep it loosely held together. that contributes to the properties of metallic solids. Metals have varying hardness. Some are pretty hard, some are really soft. You can smush sodium around with your butter knife, but iron is much harder to dent. They're malleable and ductile because that flowing, moving electron delocalization that holds the whole thing together can reform into all kinds of different shapes. If you hit it with a hammer or stretch it, it'll just take a new form and kind of reorganize the bonds that hold it together. They have varying melting points depending on how many valence electrons are there and exactly how the thing is stacked together. So some metals melt near room temperature, and some have very high melting points. They conduct as a solid or as a liquid, and that's because the delocalized electrons aren't stuck in any particular bond, or they're not part of any particular ion, and so they can flow through the crystal any way they want. And if you melt it, well, they're still available. And metallic solids tend to be lustrous, which means shiny. All of these electrons that are free to move around have a lot of different energy levels they can jump into. So practically any wavelength of light that hits, there's some electron in there that can jump into an energy level and absorb exactly that wavelength of light, and then jump back down to ground state and give that same color of light back out. And so, if you look in a shiny piece of metal, like a mirror that's backed with silver, you'll find that you see every color really nicely. Not all solids are crystalline, as it turns out. Crystalline solids, if you cool them down, so this is heat removed on this axis, you find that in the liquid state, they go down steadily according to their specific heat. And then they settle out. And eventually what happens is they'll reach their melting point, but most crystalline solids, when you cool them, will actually supercool a little bit, then they'll come back up and then reach that flat spot where there's a phase change. So this is liquid up here, and then this is phase change. This is dynamic equilibrium, so this is freezing that's occurring on this flat line. And then once it's all frozen, it cools down according to specific heat when it's a solid. Now there are some substances that we think of as solids that really aren't. And as you cool these things down, they cool down like a normal liquid would, and they sort of gradually flatten this curve out. The cooling slows down, but it never actually really reaches a melting point. So these are called amorphous or non-crystalline solids, or sometimes they're called glasses, because a very common example of an amorphous solid is glass. It's really a liquid. It's called a supercooled liquid. It has the characteristics of a solid because the molecules have not been able to make it to their crystalline sites because they're just too big and long. And so on their way to migrating to normal crystalline sites, they just sort of freeze because they don't have enough kinetic energy to move anymore. And you get this solid that doesn't behave like a solid, so it's really not. When you break glass, it breaks in jagged, irregular, not predictable shapes. You break a piece of salt or a piece of crystalline glass, and you get nice straight edges because you're breaking along crystal lines. Non-crystalline solids don't really have them because they aren't crystals, and so you get irregular, odd-shaped. Our last topic today is called the band theory of bonding. This is kind of difficult to grasp, but it explains a lot about why solids exist the way they do. We learned about molecular orbital theory earlier with single pairs of atoms bonding to each other. And so we had these energy levels. But if you have many, many atoms very close to each other, the energy level that you get doesn't have just a few lines. It in fact has many, many, many lines that are so close to each other that they're indistinguishable. So if you have two atoms, you get this kind of very distinct pattern. 4 atoms, this many lines. 16, this many. But if you have a whole entire mole of atoms, all fairly close to one another, their molecular orbital energy levels merge together and they make bands. And every atomic orbital is reflected with a band in the solid. Subvalence bands, bands that are lower than the valence level, are called localized or interrupted bands. And there's no conduction of electricity possible in these bands because the electrons that are in those bands are bound to one particular nucleus only. So this is a diagram that's often used to describe band theory of bonding. This is sort of like one line through the crystal, and the little pluses down here, these are nuclei that you're seeing. Between each nucleus is a sort of a dead spot. It's called a potential well, where electrons can't escape. You can think about this as a sort of a mountain in between the two nuclei of energy, and electrons that are in this band, they can't move to another spot. They're stuck with this nucleus only. And so that band, which I'm sketching in here right now, is an interrupted or localized band. And that's the lowest energy level band, so that's a 1s band. And then the next one is a 2s, and those electrons that are in there are bound to their particular nuclei as well. Every one has its own nucleus that it's stuck to, and so they can't move. And this is the 2p, and same thing, that band is interrupted. But when we get up to the 3s band, you can see that that potential well doesn't reach all the way up through that energy level. And so this band is uninterrupted. So the band that contains the valence electrons is called the valence band, and that valence band and every band above it is going to be uninterrupted, delocalized. So the electrons that were in that band have the possibility of moving, if there's room. Uninterrupted bands that are totally vacant or partially vacant are called conduction bands, because that's where electrons can move around through the crystal. So let's take a look at sodium. Sodium has these bands, 1s, 2s, 2p, and 3s. The 1s band is completely full, so I'm going to kind of shade this in real quick. The 2s band, also full. It's a non-valence band, and it's interrupted. 2p is full, because sodium, remember, is 1s2, 2s2, 2p6, 3s1. So I'm going to fill that 2p band with electrons, and all those three bands are interrupted, so no conduction would be possible no matter what. Now, 3s is only half full. This 3s band has room for enough electrons to absorb all the electrons in the crystal that would be in that band, which could be up to 2 per atom. But there's only 1 per atom, and so this thing is really like this. It's half full. I'm not going to shade this in. I'm just drawing the upper boundary. So this band is half full of electrons. There's room for twice as many electrons in that band, because every sodium only brings 1 electron to that band. This is a partially vacant band. And so sodium conducts electricity because these electrons that are represented by this shaded in space can get up and move to another spot. So if I put a plus down here and a minus down here, hook up a battery to a piece of sodium, the electrons are going to move through this crystal towards the plus. That's electricity conduction. That's current. Even solids that have a full valence band might still conduct electricity if there's overlap between the valence band and a conducting band that's above it. Magnesium would be an example of that. So here's the 1s, 2s, 2p. They're all full and interrupted. But in magnesium, the 3s band is also full, because magnesium is 1s2, 2s2, 2p6, 3s2. It's sodium's neighbor. So this band, this 3s band, isn't half full anymore like it was with sodium. It's completely filled with electrons, and so they're not able to move. It's not a conducting band because it's not partially vacant. However, the 3p band in sodium overlaps with it, so it's actually in the same energy zone. So these electrons can jump up into the 3p band, and then they can move. They can conduct through the crystal. So if I put a positive charge and a negative charge on opposite ends of a piece of sodium, those electrons will jump up into that local. Those electrons will jump up into the vacant band and move through the crystal. Things that we think of as insulators have a large band gap between the valence band and the closest conducting band. So you can think about it this way. I'm going to ignore everything that's non-valence here and just focus on the valence band. Let's say that this band, this first valence band, this first uninterrupted band, is completely full with electrons. But the gap between that band and the nearest available empty band, which would be a conducting band, is so big that these electrons cannot get up there. They cannot jump up there, and so there's no conduction possible. So things like sulfur or selenium, things that are insulators, non-metals typically, have these large band gaps, and so no conduction is possible because everything is either full or interrupted. Semiconductors are in the middle. Semiconductors have small band gaps. They're not huge, not insurmountable. So electrons may occasionally be promoted up to the conducting band if they're given a little extra energy, a little oomph to get up there. So you heat them up, suddenly they become conductors. So here's an example of that. So again, I'm ignoring all the non-valence bands down here. The valence band, right up here, is completely full in a semiconductor, but the band gap between this full uninterrupted band and the nearest unoccupied band is so small that if you give this a little extra energy, these electrons can hop up in there and then begin to move through their conducting band. So that's why semiconductors sometimes conduct electricity and sometimes they don't, depending on the conditions. Now, rather than heating up and cooling down semiconductors to make them conductive or non-conductive, some inventors have come up with another way. So we're going to take a look at, this is not on your notes, but I want you to just look at it to try and gain some understanding of something that's actually very important in your world, whether you think about it or not. Semiconductor doping is made when you take a crystal of a semiconductor, like silicon is what we're using here, and as you build the crystal, you throw some impurities in there. You drop in it some atoms that aren't silicon, and they incorporate themselves into the crystal. In this example, the semiconductor is doped with atoms that don't have as many electrons as silicon. So boron would be an example because it's on the group that's just left of silicon, so it doesn't have 4 electrons. So the bonds that are made between silicon and boron, they're missing something. All these bonds are pairs, electron pairs, between silicons. But this is only a single electron. It's not really a bond. So there's a hole there, a positive hole. And here's another one where another silicon and boron are attached. Boron can attach to 3 silicons. It's got enough electrons to do that, but there's a hole here. That's called a P, or positive, type semiconductor. Electrons from the outside world could jump in here and fill those holes. They're in fact attracted to those holes because they're positive. So here's how that translates to band theory. When you build the crystal, the full non-conducting band suddenly becomes not full because you have these vacancies, you have these holes in there. And so your previously unconducting band becomes a conductor. Another way to build this crystal is to dope it with atoms that have too many electrons, and that creates a different situation. In this case, we're using arsenic, which is one group to the right of silicon. Arsenic doesn't have 4 electrons, it's got 5 valence electrons. So it makes its 4 bonds with silicon, and then there's an extra electron floating around in the crystal. This is a negative, or N-type semiconductor. In band theory terms, how this works is you still have that filled molecular orbital, but now you have extra electrons. They can't go in there. So what they do is they hop up into this conduction band, and now they're able to move around. Remember, the band gap is pretty small, so it's easy for these electrons to get up there. So conduction happens in the empty band. The previously filled band is what conducts in the P-type semiconductor. Now here's how these things are useful. When you grow the crystal, you can grow the 2 of them together so that they're attached to each other and make what's called a PN junction. A junction is just a meeting or a joining place. So here's a PN junction. The positive has got all these holes, and the negative has got all these extra electrons represented by these kind of magenta spheres. And you can see what's happening here is that some of the electrons are already leaving their spots and migrating over into the P-type semiconductor because it's attractive to electrons. Now that can happen if you have negative charge over here, but only to a certain point. If you take this PN junction and you put it in an electrical circuit, two different possible results can happen. If I have my positive terminal over here and my negative terminal over here, current will flow because electrons are attracted to the positive battery terminal. So they're going to jump out of the N-type semiconductor, migrate through these holes, and then leave the crystal. Holes are then going to migrate this way because they're attracted to negative. Now, it's hard to think of a hole as being a thing, but holes actually move through the crystal. This is what's called forward bias, and current will flow in the direction of forward bias. If I hook it up the other way, however, I have what's called reverse bias, and that inhibits current flow. Electrons are attracted to positive charge. So if the positive terminal is over here, these electrons are going to move towards the far end of the N-type semiconductor, and the holes are all going to move towards the negative end of the P-type semiconductor. And in the end, you have no electron flow. This device is called a diode, and diodes are very useful in electrical circuits because they're like check valves in a plumbing circuit. They allow current to flow in one direction, but they keep it from flowing in the other direction. And there are a lot of different ways that can be used. Let's take a look at a little simulation that might make it easier to see what's going on with diodes. First of all, we have a band diagram off on the left here, and here's this little circuit. So here's the positive terminal of the battery is right here. The negative terminal of the battery is over here. So electrons are going to move away from the negative around this circuit this way towards the positive. And then here is a piece of silicon, basically. Let's see what happens when I drop in a P-type impurity in there. The electrons flow through there. If I look at the energy level diagram, what's happening is the P-type semiconductor leaves holes. You can see the holes are right there and right there. And electrons are attracted to those holes, and they just move right through the crystal, and current is conducted. I'm going to clear that out. Now I'm going to put an N-type semiconductor in there. Again, we see that there's current flow. It happens in a different way. What we've really done is we've put enough charges in there that now we're up in that unfilled or partially vacant band, which has plenty of room for electrons to flow. So there's current. Now I'm going to change the situation. I'm going to put in two segments. So this is a PN junction, a diode. We have both energy level diagrams over here on the left. One I'm going to P dope, and the other one I'm going to N dope. Current flows, but only for a very brief period of time. Let me reverse that. I'm going to clear the dopants out. Now I'm going to put an N-type on the left and a P-type on the right. The electrons flow into the conducting band, drop down into the partially vacant band of the P-type, and they just keep on moving. So current flows in this direction, but it can't flow in the other direction. If it were possible in this simulation to just pull the battery out and flipping the battery around, current would stop right now. Current is allowed to flow in one direction but not the other. That's the function of a diode. Now, there are some diodes that emit light when current flows through them. They're called light-emitting diodes, or LEDs, and I'm sure you've heard of them before.